using them side by side as I showed you, but really, yeah, trying to combine the different data. I just, yeah, you can probably see that this is the typical picture which was in the newspaper from Singapore. So AOD would be an optical effect. So I think it's really clear that there is a linkage between the particle mass, PM2.5 mass, which you see on the ground in relation to the AOD, to the satellite AOD, which is at the visible wavelength as 550 nanometer very measured. But I stole our picture from a presentation which was given by Dr. Chin. He's a modeler in May at the Living Planet, which was an ESA conference, and I think this nicely, these are model results, but it nicely illustrates that these are daily variations of PM2.5 ground, and on the right side you see A. And for some of her sites, the PM variations through the day and the AOD variations throughout the day correlate very well, and they got a correlation coefficient of like 0.8. I can't really see it here, or even 0.9 or something. But then on other days, I think they see even a total anti-correlation. And when you're down here, see that can be that the aerosols, which is satellite seas, are really higher up. They are not affecting at all the surface. So AOD to PM is a pretty tricky bit. But yeah, so it's not only the AOD, but you need additional information. But coming back to this picture, I think it's quite interesting times, because we will get this geostationary satellite, and then you get really AOD on an hourly level and not once a day. And from that, you can get more information really for in Europe and the US. And but you have to be clear that you're combining, or that you want to retrieve PM, or you want to get an estimate of PM, and which is measured mostly on the dry phase, but the AOD is an ambient one. So the AOD is the total color. It's an ambient quantity from the ground to the top of the atmosphere. It's an optical property, and it depends on the particle size, the composition, the water uptake, and the vertical distribution. So if you have just aerosols which are very high up in the atmosphere, it will not correlate with the ground-based information. So it's a tricky business. Yeah, and but there are relations. If you would say, and assuming the cloud-free sky is very distributed boundary layer with no overlaying aerosols and aerosols that have similar optical properties, then you can relate a PM. It's a function of, or it's a combination of boundary layer size, the ratio of ambient and dry extinction coefficient, mean scattering efficiency, so the size is going, so and the relative humidity. So there is a correlation which you can use under these conditions, but these conditions are tricky. So that's why people are coming into modeling and machine learning. Just a very, very quick few examples of how people wanted to correlate AOD to PM. I think maybe 10 years ago, it was people got very excited because they just saw it's a linear relationship. Then multivariate method, machine learning is more and more used to that. Some people have tried to retrieve PM 2.5 directly from combination of satellite sensors. Philipp will show you some more about data for using where they use the scaling approach, and we had a project with colleagues from Romania. They used the full physical, optical, and chemical modeling to trying to convert that. I think this didn't surprisingly didn't work so well because, but I just yeah, this was I think 2003, and people get super excited publishing things like, oh, there is a linear relationship between AOD and yeah, for this side and for the of course it works. But then I think they also say satellite observation. I think it was nice to. I started working with AOD and PM a little bit in that area, and then I stopped there for 10 years. Didn't do anything about that. But it's nice to recapitulate because these are you see measurements in the US or the AOD and PM. In the correlation here, you see that at some point some coast is very nice and the other coast doesn't really work well. So, but they were really optimistic during that time. Satellite aerosol observations, which are particularly helpful in tracking long-range transport, can overcome some of the limitations of surface monitoring networks and enhance daily air quality forecast application solution. I think this was super optimistic, and I don't think this worked out. But then I think it gets a little bit better when you put in multivariate approaches. You use AOD, temperature, planetary boundary height, water, wind speed, relative humidity, cloud fraction. Then you can get better estimates. But these also didn't work everywhere, for example, and you see some sites work better and some sites work less, and it's not super. There is a correlation, but it could be actually better. It varies with time, the year. But this is an example where people try to estimate it directly from the satellite. They try to combine spectrometers with images and directly retrieve the PM 2.5 and give that out as a product. That's a paper from Thomas Holter-Popp now, which developed this synergetic retrieval, and I was doing some validation of that. And this validation, we looked at those output against image station. But at that time, the satellites were really giving very poor information. So you just had these small spots which are basically not very useful unless you're really a nerd and were interested in these things. But then I think it also some of the areas had better correlation, some of the areas had worse correlation. So I don't think it was not as successful as they hoped. But this is also a little bit depending because they had very poor resolution satellites. Then the machine learning, I think this is just I think this was one of the first papers where they used neural networks, and there are now maybe hundreds, I don't know, at least 40 or 50 papers out on machine learning and AOD. It got very, and I think it's a good, it's probably a good set because you can throw in all the variables which are needed, and they really clearly see that with a simple correlation, you had a correlation coefficient of 0.6. It gets better in their thing with the multiple regression, and then the machine learning did better. I have not worked with machine learning, but I think this is a good application for it. I believe. Then I think this is something Philipp will talk a little bit more about. Show you some examples. This is the scaling approach where you use the ratio or the model, you let the model decide on the conversion of AOD to PM. So this is the factor. And then the satellite just basically calibrate the absolute value of the model conversion. And there is one operational or one product out from which you can use data, and I think that Philipp will show you some more examples of that. And just to finish this part up, this was the study we did a couple of years ago, a few years ago, together with the Institute for Optoelectronics from Bucharest, and they used full physical model with all the aerosol properties and used really calculated the conversion factor, and this is based on the Severi AOD with the Polish retreat. Then this was taken in by these guys from Margarele and they calculated lookup tables and retrieved the conversion factor and calculated the 0.5. The correlation was, unfortunately, I think, one of the things is here. I think you only get out what you put in. So I think they modeled this mixture simulation of compound aerosols, and they didn't put in dust, volcanic ash, and so the output is only represented for the particle type, which means that it's if you then compare to the ground station and you are, for example, at coastal region, you definitely will get very bad results because you haven't got the speakers. So it works very nice at these stations which are homogeneous in the city. So the red one is the whole satellite pixel, and here it's a mixed information where it didn't really work. But in total, I think their results were better than if they would have just used a model, but they were quite still not very convincing. So I would think, in my opinion, this multivariate regression and the machine learning is a very promising approach. And I think also this simple ratio, which Philipp shows you some more, is
Yes, so I'll be your entertainer for the rest of the afternoon. It's going to be a tough job, I think, because it's a Friday afternoon after a long week, and some of you, for you, so and some of you had like 3 hours of sleep or so last night. So we'll see how it goes. No, but so the plan is that I just show a couple of slides here to finish up this chapter on the conversion to surface PM2.5. This is not really theoretical, but showing you a few pretty pictures, because we had a study in India with the World Bank a few months ago, and so looked at this Van Donkela surface PM2.5 program. We have Ajit here, who could probably tell us a lot more about this because he was born in that area. So please excuse my ignorance about this area, but we'll. I just wanted to show you a couple examples. I can probably skip this because Kerstin already mentioned all this. Basically, so we used an existing product from a NASA group led by Aaron Van Donkela, and so they basically combine. Actually, I should go back. Right? They combine several AOD products. So they combine something from Modis, AOD from Miser, and Sirius. These are all different instruments. Combine all this stuff together, weighting the uncertainties from the different instruments together, And then they convert this AOD to surface PM2.5, and they use model information from geochem for this, and they use also surface. So they really use all kinds of information jointly to get the best possible product. And it came out very recently, and so we were interested in looking at this for a case study in India. They have it now at monthly average data, so you don't get daily information, just monthly averages at about 0.1 degree of resolution, so about 10 kilometers. So this is an example of what this can look like. This is for the Indian state of Uttar Pradesh, and here on the western side is Delhi. This is where Ajit, you're from, right? So you are exposed to this kind of pollution level. So you cannot read the numbers here, but sort of the red area in the entire center, this is 100 microgram per cubic meter, PM2.5, and this is a 10-year average. So this is something that we don't really see much in Europe or at all. So I was really surprised to see that over such a long period. So you can see that it decreased towards the south, towards the north. But what we were mostly interested in is looking at sort of the temporal variability. So you can see that here, this is just 12 months throughout the year. So you see sort of the really high PM values in the winter months, and then you have the monsoon, the summer where it goes down. See that here also in the plot on the top. So we have 10 years of this PM2.5 data with a nice seasonal cycle, and then at the bottom we have like the annual averages just to see if there's any trend. In this case, there wasn't really a we did the same for another state. This is the neighboring state called Bihar. It's just next to Uttar Pradesh. It has quite similar, but a bit lower overall. But what I really want to show is this. So we compared basically this surface PM2.5 product from NASA against the station observations that they had available in Uttar Pradesh. And here's sort of a time series that you see for the overlap period. So ranging from 2017 to 2021, in red the satellite data in concentrations of PM2.5 and micrometer, and in blue the station average. In this case, it's averaged over the entire state. So the overall levels matched quite well. I was very pleased to see that. I did not expect this, considering how high the uncertainties are in the AOD product and in the conversion process and so on. But that was really nice to see. We also then plotted a scatter plot to see how the two things compare with each other, and these have a really high R-square of 0.94. Now, but keep in mind, this is monthly data. So if we average things over a month, it will always reduce the random noise a lot, and you will always get better results. So if you did this on a, let's say, daily level, it would probably be quite different. Yeah, something like this. This is not daily level, but this is just for individual stations. Here you see it for each of these panels is one station in India, and you can see a little bit how the slope varies, but the correlation is pretty much the same for most of the stations. So it doesn't vary too much in terms of quality, but you do have some different relationships from station to station. So this is all I wanted to say about this one section of the AOD to PM conversion. And now I want to talk about the main thing that I wanted to talk about to you today, and that is the combination of satellite and ground-based observations. And I know that most of you are interested in these sensor networks and so on, so I think this will be quite relevant. I wrote here with small detours because on the way I will talk about a lot of things that are not directly related to satellite data, but they are relevant for this combination. So, for example, data assimilation at the urban scale, for example, but also things like downscaling of satellite data to improve the spatial resolution of the data. Yeah, I should also mention that most of the things I will talk about now is more local scale. So this really reflects, I talked about it with Kerstin, reflects our two different departments that we're in. We are focusing a lot on the global, regional scale, and our department focuses a bit more on the local scale. So enough of that said, I want to talk about 4 approaches. The first one is looking at geostatistics. How can we use geostatistics to fuse station observations with a model? And then that's sort of that forms the foundation then for the second topic, which is urban scale data assimilation, where we also then can bring in the satellite data. The third one is ML, machine learning based approaches. There I don't mention too much, actually just a case study from a PhD student of ours that works on this topic. And then the last topic is downscaling, which is not so much about the combination, but it's a pre-processing step in a way to to bring the satellite data to a spatial resolution that that is more applicable for combining it with the sensor data, so that you don't have these huge spatial representativity issues anymore that you normally have when you try to combine a 5 by 5 kilometer pixel with like 1 point measurement. All right. So the first one on geostatistics, I'd like to show this kind of simple plot here that basically shows if you want to interpolate or make a map of urban air quality, you have these two ends of approaches. If you have many observations here on the right, it's really easy. You just do a spatial interpolation and you're done, right? So in that case, a sloppy model suffices. You don't need a good model. Our interpolation is a very simple model and it's good enough. If you have very few observations on the left-hand side, so let's say only 5 or 10 stations in a city, then it's very difficult and we need a good model. And so then typically we need something like a dispersion model or something similar that can give us more information, or land use regression information, for example. We need something that can give us more information about the spatial variability. So here's an example for the right-hand side, or when we have a lot of observations. This is an example from what I mentioned yesterday, the Taiwan data set, where they have, in the entire country, they have about 15,000 sensor systems set up, and we had a little bit of collaboration with them. They send us a subset of the data, and this is just a small subset for one small part of the city. And on the left-hand side, you see basically all the sensor observations, and then on the right-hand side, it's just a simple interpolation of all these values, and you get reasonably good results because they are so dense together. But this is the exception rather than the rule, unfortunately. So normally, we need a much better model, or I call it here a priori, a much better field of the estimated spatial variability to do this. And data assimilation is the way of doing it. But in geostatistics, we can, I don't know, has any of you used geostatistics before? I know you Greek guys have used it, right? Anybody else? With pre-game? Yeah, 4 or 5, okay. Minus also, yeah. So I am not going to go into any mathematics here, but so geostatistics is just a way of, in a way, interpolating data by taking account the spatial autocorrelation. You can do it in 2 ways. Without an auxiliary variable, so really just interpolating point measurements, then we would use something like ordinary kriging, and then real power comes in when we use auxiliary variables, then it's something like universal kriging or kriging with external with several names with it. So in very simple terms, what we then do is we interpolate between all the observations using a continuous spatial proxy variable as a guide to the interpolation, because interpolation doesn't know what is happening between observations. So this proxy variable can help the interpolation along the way. Here's the just a sort of very simple scheme of how this could work. This is for the European scale from a project we had with the ET, with the European Environmental Agency. But essentially, we have used point-based observations from all the monitoring network in Europe on the left-hand side. Then we have model output in the middle, and then we have satellite data on the right. All this goes into the geostatistical framework, and now it comes a map of air quality or a similar parameter that can basically make use of the information from the various data. So, yes.
We can point out that the European Air Quality Index is down by not with the models that you have been mentioning necessarily and the data, but that's basically also the methodology. So I really encourage you to look at the European Air Quality Index because it provides also a prediction. It's not talking about that. It is really quite a precise instrument for implementation. Just that you have some relationship to that this is not something we come up with, but it's a methodology that is widely accepted.
Thank you. So again, I'm not going to go into detail on geostatistics, but essentially it boils down to this plot you see here on the left, which is called a semi-variogram, which gives you information about how points correlate with each other in space. And so you have to fit a model, a blue line to this data, and it gives you information about, that in this case, that the Stations very close together are very much correlated, and stations that are further apart are much less correlated with each other. And at some point here, toward the end, you reach a plateau, and then you basically have no more progress. So that is the underlying principle here. And on the right-hand side, you just see two examples for the urban scale in black dots. I'm sorry, it's so small here on the screen, but you get the idea. The black dots are observations. And if we just interpolate the observations without any other information, we get these really, really smooth patterns, which are not realistic in terms of air quality, particularly things like NO2, which is very, very sharp gradient. On the lower right is then the example with spatial proxy, where we use geostatistics together with a model that can guide interpolation, and then we get a much more detailed output that can typically will be a lot more accurate than just. There are many ways of doing this. Geostatistics is one that I like to call data fusion in a way to distinguish it from actual data assimilation. But there's a huge overlap between data fusion and data assimilation. Some of these methods, like 3D VAR, it can be proven mathematically that it's the same as geostatistics, just in a completely different framework. It was developed in different communities. The 3D VAR comes from meteorology, and then geostatistics come from mining. But essentially, it's all the same thing. And then there's very complex approaches like 4D VAR, so which I cannot open. You need four-dimensional variational assimilation, and it's basically takes also into account the time component. So instead of this three-dimensional space, you also have an additional time, and that's important. For example, if you only assimilate observations into a model at a given time step, then the next hour of the model will not have that information from the station anymore. But if you do something like 4D VAR, you can propagate that signal through time, and then you will have in the next few hours from the sensor observation. Yeah, so in this methodology which I show here, which we developed already in CitySense many years ago, that was like 6-7 years ago, we just basically combine a static base map with sensor observation for each hour, and then create like an hourly fuse for data fusion map. This is sort of a bit outdated now. Do it a bit differently now, but the principles are still quite similar. So here you see an example on the top left, the background, like the colors in the background are the model, and then in the front, these little squares are the observations from the sensor network. And you can see that it's on the same color scale, right? The model completely underpredicts what the sensors show, and so the whole thing has to be lifted or bias corrected up. And on the bottom right, this is the result from the data fusion, where you see that the colors from the squares and the colors from the background map match much better. And so this is what we can do with these kind of approaches, but it is still a bit limited in the sense that you cannot really determine exactly. So we get maps like this. This is all examples for Oslo, where we have sort of high pollution levels along the roads and the center of the city, for example. And then with these maps, we can then, I don't know, extract things like the pollution levels along a bike path, because we were interested in giving information to bicyclists, and also giving more targeted information to specific user groups. You can also then take these maps and calculate the exposure along a certain path, so you can calculate at this theory how much particles, how much mass of particles somebody has inhaled on a bike route through the city. Or you could potentially also predict or provide pollution adjusted routing maps, so you can route a bicyclist along a park rather than along the main roads to decrease or optimize the intake of particle matter and so on. So these are all the kind of things that can be done. Here's an example of 24 hours of these fusion maps for Oslo, so you can see basically how in the night we have very low concentration. Then in the morning rush hour, we have very high concentration on all the road links, and then it goes again a bit down to the afternoon, goes a bit back up in the evening rush hour, and that's it. And then go back. You can also see the same pattern here. This is just a comparison with the monitoring stations. And so we had sort of a nice diurnal cycle with the peak in the morning rush hour, and then a more broader peak in the evening. So this was all for NO2. The same method with the geostatistics is currently being used operationally at the European Environment Agency. We're creating these European scale maps of air quality. For PM, we are currently not using satellite data. We use basically model information, elevation models, and several other parameters that go in there, and then interpolate the observations from the stations to that extent. This is also PM 2.5. But for example, for NO2, we use satellite data. We use TROPOMI NO2 data on an operational level. This has quite a nice, it shows a nice improvement of the accuracy of these maps. So the second part I want to mention is a bit more recent work. This is on urban scale assimilation. So this goes away from the geostatistics a little bit. The principle is the same. We have sensor observation, we have model output, and we fuse it in some way. And we want to do this in a way that adds value both to the input data set. So the model is constrained by the observations, and at the same time, the observations are interpolated in space in a meaningful way. So here's the mathematics behind it. We use a relatively simple approach called OI currently. It's somewhat similar to geostatistics, but it has some advantages that are probably a bit too complicated to explain, but you have more control over how the sensor observations are propagated in space. And let's just skip the equations. There's no point in going into this. Okay, so one thing that we need for this is the uncertainty of the sensors, and I'm sure many of you have seen plots like this. This is the relative expanded uncertainty from one specific sensor. So it shows that we have a high relative uncertainty when we get close to the detection limit, and then when we have higher concentrations of the x-axis, the uncertainty decreases, and then eventually we get below the green line, which is the data quality objective from the EU. And so in this case, we would say that this sensor passes the data quality objective for indicative measurements at around where the blue line crosses the green line, so at about 30 or so micron. And so this kind of information we can use to determine the uncertainty from the sensors, which needs to go into this data assimilation process. But what is more difficult is to assess the uncertainty of the model. And uncertainty here really is a misnomer, because it's not the uncertainty just that tells you, okay, how wrong is the model at a given point in time. What it means model uncertainty in the data assimilation field is something like the map that you see here on the right. Unfortunately, it's a bit difficult to see on the screen, but basically what this model uncertainty describes here is how a signal from a sensor, so you see this, you see here this little black triangle, that's a sensor, right? It's a sensor right next to a busy highway in Oslo. And the colors indicate how the sensor will affect its surroundings. So what we don't want is the sensor affects its surroundings in a circular way, because then you get these blobs in your map, which look really unrealistic. But if you basically generate what I like to call it like the footprint of that sensor, if you generate maps like this, you tell the data assimilation framework, okay, if we have a high value at this black triangle, you should really increase or elevate all the observations there that are marked in, but all the pixels that are marked yellow, and maybe a little bit the ones that are blue, but leave everything else alone. And so when you do this, basically you limit the impact of any sensor or any observation to the areas that it's actually representative for. And the tricky thing is that for this data assimilation, or at least for optimal interpolation, you have to specify this manually. So for each pixel or for each sensor that you have, you need to have a map like this. And you can create this, you don't sit there and draw it, you just create it from the model information. You basically look at how the model for this particular hour correlates with other in space, and then you overlay sort of a distance decay function to make sure that the sensor does not affect areas in other parts of the city, for example. Here's the same map, but for a background site. and you see how it becomes a bit more isotropic, a bit rounder, right? Not entirely, but it's a bit more rounder, and that's because we're not looking at a sensor at a really busy traffic intersection anymore that has very small area of representativity, but it's a much it affects a much larger area because all the values in this area, this is mostly forested or very low pollution areas. Most of this is going to be have quite similar values. So then the footprint of the sensor changes accordingly. So when we do all this, we can do our assimilation. So here on this map, you can see the city of Oslo, and the background is the original model estimate, so the a priori we call it, and then the round little dots are the observations from sensors. You see that the colors from the sensors in the model are not in all cases agree with each other, right? So for example, here, in this case down there, the sensor measures its relatively higher value than what the model predicts. So we would want this area to go up, right? In the post-process assimilated data set. Similar over here, for example, this value, this sensor shows a value of maybe 50 micrometer or so. Yes. Whereas the model shows the true values, maybe 10 to 20. So the model is really underestimated here, and we want to bring this up, but not in like in a fashion that brings up everything at the same time, but localized and according to the road network. So if we do this, we get something like this. So you see here, the value that I pointed out over here, it has increased mostly along the road. So these values have been increased quite a lot, a little bit in the surroundings, but it hasn't affected, for example, the area here, which is background, right, which is the forested area with no emission. And so this is really important when doing this, particularly for NL2, but also for PM2.5 or other particles, because otherwise you'll very easily sort of correct this map in a way that is not realistic or not physically. Here's an example from a similar study that we did in a town called Stavanger in Western Norway. We had a deployment of 10 units. I noticed right now, by the way, that we moved quite far away from satellite data, but I promise this will be relevant later on for the satellite data as well. Because, I mean, you basically want to use both the sensors and the satellite data in the model. And for to do that, you have to basically develop a good assimilation system first. So we deployed 10 units here, and these units are the ones, I think Alena talked about them on Tuesday. These are called air sensors. They are quite big. we were quite shocked when we saw how big they were, especially when they have to be co-located at our reference site. But they're really nice in the sense that they're all open source. So they basically all the measurements you get are raw measurements. There's no manufacturer that does something to the observation that they don't. So you go in the cloud and then you don't know what actually happens to the data. So you get raw data, which can be a good thing, but it's also a bad thing because it means that you have to do all the calibration that Saverio and other subjects I talked about. So you don't get away with it. Anyway, so we have input data. On the left-hand side, we have our model information for this particular site. In the middle, we have the sensor observations. And then on the right-hand side, this is the innovation. So this basically means how what the difference is between the sensor observation and the model at this particular location. And here you see these footprints that I showed earlier for each one of these stations. So you can see how they vary. Some of them are very sort of horizontal along a road. Then on the bottom one here, you have one that is clearly a background site, since it's nearly circular in shape. And so all of them sort of will affect the model output quite differently. And then when we do this, we have the assimilation on the right-hand side and the prior or the before assimilation on the left-hand side. It's very difficult to see here the actual changes because they are very subtle, but you see definitely here an example where the sensor has sort of increased the values here along that particular road because it was a strong innovation here. And in a few other sites, you can see minor changes. This is the same thing, but just for a few hours, starting at 7 in the morning and then going to 5 in the afternoon. In the top, the model, in the middle, the analysis, so the output of the assimilation, and at the bottom the difference. You can see like, no, actually you cannot see it on the yeah, so this can be done, and now comes the question how to bring in the satellite data, because of the spatial scales that I'm talking about here. This is not tricky. We've seen from Kerstin that a lot of the product is very, very coarse resolution, right? And so the question then is how to bring that into these urban scale applications. So I will be mostly talking about NO2 here because this is what I have worked on mostly for the last year or two on a project for the European Space Agency. To some extent, results might be similar for PM, but I haven't really tested that. What I want to mention is that directly assimilating the satellite data is very tricky because it is NO2 has a very short lifetime, and for that reason, the signal in the data assimilation system decays very, very rapidly. So what we then thought, well, okay, the best way to do it might be to integrate this NO2 data from the satellite into our urban scale air quality model and use it jointly with the station data of the local sensor network. And this integration, I will talk about this in a little bit, does not happen through assimilation directly, but we change the emissions of the model rather than changing the concentrations inside the model. So the question was, to what extent can the satellite data help with calibrating the existing model? So there's a long list of requirements to do this because the model and the satellite give completely different things. So the satellite gives us a column of NO2 for the entire troposphere. So we're talking 12 kilometers roughly, an integrated value. Whereas the model, in this case, we use a model called episode, which is like a very high resolution model for the urban scale. It gives us information on layers from 12 meters to about 3 kilometers height. And the model also doesn't give us a column, it gives us just layers. And so it's not so easy to just sort of sum up these layers and call this a integrated value, because the satellite has sort of a certain, it has an averaging kernel, like a profile that sort of weights things in different altitudes differently, and so that needs to be taken into account. So we have like this long list of things that we have to do. I think I skip this here and just show it on the next slide. We have to do a temporal interpolation of these hourly model data to the overpass of the satellite. We have to project it to the different coordinate system, spatially interpolate the model output to the footprint of the satellite. We have to vertically interpolate between the different layers and then apply this averaging kernel and calculate then these NO2 columns of the model. So this was quite complicated, but in the end it's worth it. In the end it's worth it because you get things like this. So here what you see on the left hand side is a very much zoomed in picture of Tropomi NO2 column over the Oslo area. So you see how coarse the pixels are. We're talking about 5 by 3 kilometers or something like this here. But what you see in yellow is a plume of NO2 originating from the city and then moving towards the southeast. And on the right hand side, you see the same exact thing then modeled from our episode model. And both of them show the plume, but you can see that the model is slightly off in terms of the plume. It has slightly different directions. Could be due to a wrong meteorology, possibly, we don't know. But the values are quite similar. And we were really happy to see that. And this scatter plot shows this correlation between these two. So on the x-axis, we have the model output, the columns of NO2, and on the y-axis, the satellite NO2. And so we had a reasonably good correlation, about R square of 0.7. And so we were quite happy to see that, at least to some extent. Now, I'll skip that part and go directly to this. If you then do this not just for one day, like I just showed, but you do it for all the days in a year, you can make a plot like this. So each circle here represents the correlation coefficient between our model and our satellite. And you can see that in some cases, it's really, really bad, right? You have negative correlations. In some cases, it's like 0.1, 0.2 or so. And for some cases, it goes reasonably high. So it's not every day that we get a good correlation like this, but for some. So this is showing, for example, the highest correlation, I think it was where we had a really good correspondence. But I just want to mention it's not the case every time. nonetheless, if we do it for every day, we can calculate the difference between the modeled energy column and the satellite energy column. And this is what you see here on the y-axis for every day of the year, every overpass of the year. And you can see that we have sort of a variability over time, showing that our model and on the satellite show different things throughout the year. Ignore for now the first 3 months. We have like a strong bias here, and we are not entirely sure what causes this. But the rest of the year, we are pretty confident that these are real biases between the model and the satellite. So what is then very important to show is the bias that we get between the model and the satellite data. Does that represent also the bias that we get between the between the model and the station observation? Because if not, then we cannot do anything about it. But in this case, you see that we have a correlation here throughout the year between these two things. So when the satellite tells us there's a bias in the model, we can be pretty confident that this is an actual bias in the model and not just a problem with the retrieval or the processing technique that I showed earlier. So with all that said, we can then calculate correction factors because, well, actually, let me go back one more moment. For each of these days, we can calculate a relative difference between the two, and that's a relative correction factor in a way. And we can apply these to the model. And when we do this, and then rerun the model and evaluate it again, we get a change in the accuracy of the model and a positive change. So, sorry, an improvement in the accuracy. So the red dots here show for each of the stations the original emissions. And in blue, we see the scaled emissions with these satellite-derived correction factors. And for some of the sites, actually, I didn't label here what ABC is, but it doesn't matter. The point is that for most of the stations, we have a decrease in the. I'm sorry, this is the wrong plot. This is not what I want to show. Okay, the point is that the month-by-month correction improves the accuracy of the model, and by up to 20% approximately. So we integrate the satellite data indirectly by changing the emissions of the model, and then again.
How would the satellite add on? You also have the difference to the ground vector. If you would use those to correct the model, what is the benefit of the satellite?
That you can do it also in areas where you don't have. In addition, you have the benefit that, for example, when you have only two stations, quite common, then you don't really get sort of consistent bias. So with the satellite data, you have more robust bias.
You do the correction for the regional.
We do it both. I haven't shown this here, but we can also correct the emissions on a spatial level. Yeah. I think I actually do have a slide on this, but it gets a bit too deep into detail. But anyway, so this is the output from the model. Here's the original emission, and here's which I think.
No, I'm just thinking also.
Okay. So here's the model, the original emissions, and then on the next slide, this one here, it's the scale emissions from the satellite. So there's subtle differences, but definitely improvements in the accuracy. Okay, let me skip this. It's getting a bit long anyway. Yeah, this is actually the point that you mentioned, Kerstin. So we can also, so far we've only corrected the emission in time, but we can also correct the emissions in space with the satellite data. For that, we have to use an areal weighting algorithm to go from the original satellite footprint to a more regular footprint, so that we can average the satellite data throughout an entire year to go to a regular grid. And if you do that, we get something like this. Here's the vertical column density for the average of the entire year over the Oslo area. Of course, you have, for those of you who don't know, the center of the city is approximately here. We have the highest concentration. You look somewhere here in this area, right? Yeah, so we have the highest concentrations of columns here in this area in the eastern part of the city. So that all makes sense. And then we can look at what the model predicts. somewhat similar, not quite the same, but the hotspot is roughly the same. This is the surface NO2 from, sorry, this is not the model. This is the surface NO2 calculated from the satellite, which is the methodology that we'll talk about a bit later. This is the model predicted surface NO2 for Oslo. So the hotspots are all in the same area roughly. Here we have the difference between model and satellite for the surface NO2, and so we can use that information to then calculate the correction factors, and these are shown here. So in each pixel, we see here like a percentage, and this indicates basically how we need to correct the emissions in that particular pixel to better match what the satellite observed. Yeah. There's some issues with edge effects here. So the ones on the outer border, I don't trust. There's some things wrong here, but in the center, it's quite good. So third topic is, I want to talk about this only briefly. This is machine learning based approaches. And what I want to talk about is a study that our PhD student Shubita is working on. And she's trying to calculate surface NO2 from tropomi NO2 column. And she's trying to do that using machine learning. So you can see here basically what the satellite really measures is this quantity here called slant column density, and then that is typically converted into a vertical column density. And this vertical column density has a tropospheric part, which is the one that's interesting for us who are interested in air quality, and has a stratospheric part. And then what we really want for exposure applications is the surface NO2. And so going from this tropospheric column to surface NO2 is the part that is the focus of this work. So Shubita is basically training a machine learning model. We've heard a lot about this yesterday. She's using XGBoost, and she's training it with all the observations in Europe for NO2, and using other data sets as well as auxiliary information. And then the output of this is then an estimated surface NO2 at 1 kilometer spatial resolution for all of Europe. So this is not really urban scale, but it's supposed to be for all of Europe. You could probably do something similar for urban scale, but it's not focused here. These are all the variables that she's using as predictive variables for the machine learning. So we have, of course, the satellite data here on the top left, then elevation, which surprisingly has a strong importance for the learning. It doesn't make sense to me, but this is some of the things that happen in machine learning, that sometimes variables have a strong effect and you don't really understand why. And sort of, as somebody who grew up without machine learning, it's sort of a bit weird to me, and I don't really know how to deal with it. It's frustrating, but I guess we have to live with it. There's other variables. One is that's quite important is the planetary boundary layer height. So she gets this from the ERA 5 model. Then we have the solar zenith angle, which is supposed to be a bit of a proxy for day of year. Elevation deviation, she calculated this from the elevation map because somehow this also has an effect. Temperature. Then one thing is really nice, I think, is the nighttime light. So there's a satellite called VIIRS that measures also at night and measures basically where artificial lights are. And this is a really nice proxy for human activity and also therefore for emissions. And it also varies over time, so you can see basically if the city is growing. So this particular product will pick up that information and adjust the emission proxy accordingly. Then we have a simple MODIS NDVI. So NDVI is a vegetation index that tells you how green a pixel is and how urban it is. And so that is basically just a proxy for urbanness of an area. So how densely built up it is, or it's very natural to block for. And finally, she's using wind speed, wind direction, and acceleration of the wind. And it's also from the ERA 5 model, but surprisingly has not a strong effect. I was also surprised about that. And then something like we can keep the indicators of day of the year, and out of that then comes an estimate of 30. Now, this is a first validation or evaluation of the model. So the scatter plot looks okay, not great, but the mean absolute error is only 6, which is really nice considering that it's for all of Europe, and a correlation of about 0.76. Now you can tweak this a lot by choosing the right machine learning algorithm, by adjusting the hyperparameters of the algorithm. You can increase that, but it doesn't necessarily make the maps any better. So we've noticed that as well. So just because you get good accuracy doesn't mean that the maps are realistic. Here's a map that shows the error of the model over time. So we start here in January on the left. So we have relatively high error. In the summer it's lower, and in the winter it's higher again. And that is, of course, just because the values are higher in the winter than the summer. So if you look at the relative error over time, then we have actually the opposite effect, that we have the highest relative error in the summer when the two levels are typically lower, so we are closer to the signal to noise ratio of the instrument. When we have high pollution levels in the winter, we can model it quite well. Here are some error statistics for the various station types. So not unexpectedly, the lowest error is achieved for rural background stations, because they're the most representative for a large area, which is most representative of what the satellite actually sees. And the highest errors are, for example, traffic urban, which are really, really localized, only representative for a very small. So this all makes sense. Here's the feature importance. So which variables matter the most? And so the satellite data, the tropospheric M2, has the highest feature importance, much higher than anything else. But as I mentioned, elevation comes already second, and there's no real physical explanation for this, so I find it very strange. Then we have this VSA night radiance. These are the nighttime lights that I mentioned, so these are also quite important. Solar signal angle, then the NDVI vegetation index, and then a few other variables that are not so important. You can also see that in the decrease of the mean absolute error, the satellite data is also highest, but very closely followed again by elevation, which somehow seems to have a very strong effect. And finally, what she produces then are maps like these. This is for one particular day, 19th of March 2020, for example, just at the beginning of the lockdowns in Europe. What is nice that you can sort of see the hotspots, at least the major hotspots in Europe here, Paris, the IM2 levels in the Po Valley and so on. You can see Serbia here, Belgrade, I guess. So all these patterns are available. We have, did I point at the wrong thing? That was Belgrade, okay. And these gray areas here, by the way, these are areas with cloud cover. So this is something that we cannot get around with satellite data, or not the type of satellite data that we use. When there's clouds, there's very little we can do. At least dense clouds we cannot work with. And then as soon as one of the predictor variables in this model is missing, we cannot really calculate a good value. So here you can see the weekend effect. On the top here is a map for Germany for a Sunday. And then on the lower right is a weekday, like next Monday, I think it was, where you see much higher values. And then if you do this for an entire year, you can see the effect here as well. You have Monday to Friday relatively high concentration, and Saturday, Sunday are low. And so this is something that the model thankfully picks up. You can also see how 2019 was quite a bit higher than 2020, 2021, presumably due to the pandemic effect. So these kind of things come in here. Now, this was not really machine learning to directly fuse the sensor observations with the satellite data, but it in a way fuses the station observation with the satellite data indirectly, because you train the satellite data on the station observation. So I think it still fits in there quite well. And it will be interesting to see what else comes out of this, particularly when we go to higher spatial resolution, for example, for the urban scale.
Okay.
Yes, you can. You know what? Let's have a break now, and then I continue after this. Yeah. Okay. Sorry. I'm nearly done. There's like there's just maybe 15 more slides or so, and then we can do a practical.